bond between teachers and students at all levels, and it's true at the graduate level of biostatistics education as well. So Juwon Song, our speaker today, got her Ph.D. in biostatistics in 1999. I think that you and I probably met in 1995, roughly, when I had just started as an assistant professor, joined with the Department of Psychiatry and Biobehavioral Sciences, and Juwon worked with me as a graduate student researcher and did dissertation work on multiple imputation problems in high-dimensional settings, and it was a successful enough operation that she stayed on at UCLA for, I believe, 4 years after that, joint between Department of Biostatistics and what was then the Center for Community Health. And so, as you saw, she and Mary Jane worked together on projects, and a number of familiar faces who've collaborated with Juwon over the years. Then after that, she went to an assistant professor position at the University of Texas MD Anderson Cancer Center for about a year, and during that time there was an announcement for a tenure track position at her alma mater, University of Korea University in Seoul, and she applied and got that position, and she's now an associate professor, director of the Center for Data, I'm going to get the name wrong with that, in multiple leadership roles there, and is on sabbatical leave, and is a visiting associate professor this year in the UCLA Department of Biostatistics. So it's great to have you back.
That's quite a nice introduction. Thank you very much for giving me an opportunity to give the presentation today. Actually, this talk is special for me. It has a special meaning for me because, as Tom introduced, the Center for Community Health was my first job. And I actually, after I received my Ph.D., actually Dr. Rodram was the committee member of my Ph.D. dissertation as well. And after receiving my Ph.D., actually I worked here for several years. And I can still find familiar faces here and over the office over there. And so I'm very glad to have the opportunity to have given the talk and feel like I come back to home. And today, actually, I will give the brief presentation. Title is the multiple imputation for missing data in KLoSA. Actually, KLoSA is the Korean longitudinal study of aging. And this talk is not that theoretical, not much of the symbols, and I just try to share my experience about the imputation. Okay. First, actually, since my talk is about the missing data, I will introduce what's the missing data and what the missing data mechanism is, and how the missing data mechanism is related to handling the missing data. And another, actually, the point is to handle the missing data, I used multiple imputation. So I will briefly introduce the imputation techniques, what's the meaning of the imputation and how we handle that. And third and fourth is the major part of the study, which is the missing data problem in the KLoSA study, and how we handle the missing data by using the multiple imputation. The first part is about the baseline data, and we extended to the first follow of this longitudinal study. And I will show some simulation results, and I'll finish with the short discussion. This is a typical data set with missing values. So normally we have like this kind of rectangular data set, and hopefully it doesn't have this cushion. So we have, once we have the field data set, we are fine. But unfortunately, many cases, actually some of them may not be measured due to a lot of reasons. due to the non-response, due to some other reasons. And we cannot see some of values. So this is the typical shape of the missing data set. And problem is, once we have all these values without question mark, so if we have the filled set of data set, we can't use whatever analysis we want. But due to this question mark, which we do not know, actually our analysis is limited. To handle this missing data, we use short notation. Well, normally we call that rectangular data set as y, or x, whatever. But I will call that as the y. So y means it's just n by p data set. So have n units, n observation normally, and for the p variables. So we have this data set. I will call that as y. But unfortunately, we do not have the whole information for the y. We only have the observed part. So we call that observed part of y as y-ops, which indicating the observed component of y. So it means it's just the whole portion except the question marks. And of course, the question mark portion, which is called as y-miss. So y-miss is the unobserved component of y. So of course, altogether, y-ops and y-miss is y. And we also have another information. There it is. In addition to the values, data values, we know which one is observed and which one is not observed. That's actually expressed as the missing data indicator matrix. So which part of the data is observed, which part is not observed. So that is expressed as the just 0, 1 values. If it's missing, we call it 1. If it's observed, it's 0. And actually, this missing data indicator has the same format, same size of the data set, but just have 0 and 1. Whether that's observed, all this part is 0, and this portion, which is not observed, is 1. So we actually, for the missing data set, in addition to the data, we also have another portion, which is the missing data indicator portion. So whether we have certain values, as well as whether that values are observed or not. That's the fault. And we have the notation for the joint distribution of the data, y-ops and y-miss altogether is y, and we express that as just this kind of distribution. And here they are indicating the known parameters of this model. And we need another portion of the distribution, which is the distribution of the missing data indicator. So which part of our data is observed should be modeled. That part is also expressed as conditional distribution of m given the data set. And this is the parameter related. So since, well, of course, for the fully observed data, you don't have to have this portion because everybody's observed. Everybody's values is, of course, 0. So no need for this portion. But since we have missing values, we need to model both the data part as well as the missing data part. So normally, full model treats m as the random variable as well as the data set, and we have to have the joint model of y and m, which is expressed like that, or expressed by using the marginal distribution of y as well as the conditional distribution of the missing data indicator given the data. And more complication is, unfortunately, you do not have full information about y because we only observe the quotient, which is the y-ops part is observed, but y-missing part is not observed. So, frankly, our observed data model should be this format. So instead of having the y, total y, since we didn't observe y-miss, we only have observed y, and we have the information which part is observed and which part is not observed. And altogether, we have to model. But problem is actually to have this portion, we have to actually integrate out the missing portion, since we do not have the portion. and integration gets complicated. And so, if normally people express this one as this kind of joint modeling, pretty much like that. So this joint distribution can be expressed as the distribution of y and conditional distribution of m given y. And to have actually nice representation, actually we put the assumption to this portion. And of course, once we have the observed data, we have the likelihood, and we do the inference based on this likelihood. And the point is actually, at this point, so we actually introduce the missing data mechanism. And missing data mechanism become very important because this part gets very complicated because it includes integration of the missing data part. So to have this portion become simpler, we put some assumptions. So normally, actually, there are three assumptions. First assumption is called as the missing completely at random. Actually, Rubin introduced this notation. And first one is the missing completely at random assumption, which means is the distribution of m given y, which is this portion. Distribution of m given y. This portion puts the assumptions that does not depend on y at all. So means it's actually whether you have the missing data or not doesn't depend on any value of your data set. So means it's actually your missing items are just a subsample of all data values. And if we have that assumption, so this portion actually does not depend on this part. And this portion is not related with y miss and moves out. And this integration is not related with this portion, only related with this part. So you can't just have the integration over that to the y miss part, means it's just you are having the information about y ops given data. And your inference about data is just based on y miss. Of course, there's one more assumption is required. I will talk about it. Similar actually assumption, but more realistic is the second one. Because first one, of course, is nice assumption, but it's not realistic in many cases, unless actually it's the missingness is designed by the experiments. No, so actually we weaken the assumption, and we say that actually distribution of m given y only depends on the observed part of the data set, not the missing part of the data set. This is expressed like that and called as the missing at random. Many people got confused between the missing completely at random and missing at random, but there's no completely, so it's missing at random, or called as MAR assumption. And similarly, if we have this assumption, this portion does not depend on y miss, so does not relate with the integration of y miss. So goes out, and our inference gets much simpler. And of course, if you cannot put these two assumptions, you have to stick on the NMAR, which means is your missingness depends on both y ops as well as y miss. So if your missingness depends on your observed part of data set, which is called as NMAR, and if you have this assumption, unfortunately, you have to model this portion in your analysis. And luckily, if you can stick on these two, and then if we can say that this parameter and this parameter is distinct, so does not relate with each other, we call that, actually we can't ignore this portion of the model. So we call that missing data mechanism as the ignorable missing data mechanism. And that's the reason, actually, most people just stick on the ignorable missing data mechanism, because unless you assume that the missing data mechanism is ignorable, and then otherwise, if you cannot assume that, you have to model this portion, and it gets much, much complicated. And at this point, people might ask, how we know our data follows the MAR at least? And well, actually, since according to the MAR, you can actually depend on the observed part of your data. Actually, if you can include the variable which is related with missingness, and then your model actually will be very close to the MAR. So just by looking at the variable, you cannot say this is the MAR or this is not. But by including more variable, you may be able to reach closer to MAR. For example, income is normally, just the income itself is normally follows the NMAR. Well, income is the kind of typical variable which has a lot of missing values because people does not want to release their income, and they tend to refuse to answer more. And income itself is normally, the missing data mechanism of the income normally follows the NMAR because especially the income, for income case, the people who actually earns a lot of money tend to refuse to answer their real income. Or some people who doesn't have any income feel shameful may not answer. But kind of in the middle, people tend to answer more. So actually, income itself might just follow the NMAR, missing data assumptions. However, if we have more information about related with income, for example, incomes are related with education and age, and probably gender and other job categories as well. And if we have those information in the same level of age, same level of education, same probably similar category of the income the job level, their missingness might be just one. So it goes to the MAR. So actually, analysis of the missing data pretty much assumes the MAR assumption, and we have to have the variable which follows the MAR assumption closely. And actually, the missing data imputation I will discuss today also assumes that missing data mechanism follows the MAR. And actually, I try to fit that assumption as much as possible. Okay, and then actually I will just briefly introduce the imputation. Of course, imputation is not just anything special. Imputation just means all the method to impute missing values. And how we impute missing values, how to choose the plausible values for the missing values is more important. So imputation itself is any technique to fill in the missing values, but how we impute the plausible values is more important. And of course, there are a lot of methods as suggested. Imputation based on explicit modeling, or imputation based on implicit modeling, and mixture of that. Of course, the imputation based on the explicit modeling just means that actually our imputation model is from the formal statistical model, sometimes normal distribution, sometimes other distribution, or even the mean imputation, probability imputation, all this regression imputation. All these actually assumes a certain distribution, and we call that as explicit modeling. Or implicit modeling is also very, very popular. The point of the implicit model is we are not focused on the distribution of the data stock. Rather, actually, we try to pick the most plausible values for these values. And content imputation is the most popular implicit modeling. And nowadays, actually, composite method, which actually brings the advantage of the explicit modeling as well as the implicit modeling, is also very popular. And today, I actually, for the KLoSA data, we chose this composite model, which is the imputation based on predictive mean matching. And how we choose that, I will discuss that. some people say, what's the multiple imputation? And what's the special for the multiple imputation? Actually, nothing special. Only difference is whether we impute missing values with one value or more than one value is the difference. So normally, if you impute one value for your one missing value, we call that as a single imputation. But problem of the single imputation, which means is just for the one missing value, you just fill in this with one part of values, and everything looks fine. But problem is, once you fill in the missing values, your imputed data set does not say which one is originally observed, which one is not originally observed and imputed. Because actually your observed values are really exact value, but your imputed values may not be the exact value. Of course, with high probability, it may not be really exact values. And once you actually ignore that difference between the imputed value and observed values, you do not have enough imputation uncertainty. Simple idea is this. You have 30% of the data missing, but you filled in by using whatever imputation. And then your data looks like 100%. And real information you have is just 70%. But since you use the imputed data set, it looks like you have the 100% of data sets. And once you have that the imputed version of data and the analysis, your standard error gets much smaller because you exaggerated 30%. So your standard error tends to be underestimated and may cause the problem. To avoid that, actually there are two big approaches. First one is actually try to avoid the bias of the standard error. So since standard errors are underestimated, actually try to get the unbiased or nearly unbiased variance estimates, which is actually two directions. First direction is just to try to calculate the real, true, appropriate variance by theory. And of course, this gets complicated if you have complicated data or imputation model. So people actually tend to move to the second direction, which means is use the replication method, such as the bootstrap resampling method, which creates a number of replicated data sets. So we have the data set, we have the resample from the data sets, and estimate the variance based on reproduced samples. And this approach is one approach. And this problem of this approach is usually for the bootstrap samples, you have to sample like several hundred or 1,000. So you have to repeatedly sample and get the estimates. And using the estimates of 100 or 1,000 replicates, you estimate the variance estimates. Instead of that, you can use the multiple imputation. So instead of 1,000 replicates, you can have more than 2 plausible values imputed for each missing item. So for example, if this part is missing, instead of filling in the missing value as 1 plausible values, we fill more than 1 m plausible values. And of course, these m plausible values might be all the same or might be not. If you can guess this value exactly, these all m values would be exactly the same. But you may not be able to guess someone's income with 100% certainty. And then we can guess their income might be 300, 400, 200, and so on. Those uncertainty explains our uncertainty about the missing values. And multiple imputation produce multiple sets of data sets. Everybody is scared. Why we have 5 sets of data sets? and those differences indicating the uncertainty about that values. And of course, we do not have the analysis based on 5 results. So I have 5 imputed data set. Here it is, the results. Your income, the average income might be 300, might be 301, might be 302, something like that is scary. Of course, we can't actually combine all these results and provide only one assumption. That's the combining the multiple imputed. And I will not discuss about that today. But using this kind of multiple sets of data sets, actually standard analysis can be conducted for each imputed data set, and we can combine the results. And this tends to give much unbiased as standard errors. Of course, there is disadvantage. Since you have 5 sets of imputed data set, you have to repeat the same analysis, and you have to combine the results. That's additional work is required. So there's advantages and disadvantages. But anyway, once you have missing data, your analysis gets complicated. So either you are having the multiple imputation, or if you use the single imputation, you have to actually adjust your standard errors to do the correct analysis. And today, I will actually show the multiple imputation approach for the KLoSA data sets. And of course, same as the KLoSA data, many popular multiple imputation assumes that missing data mechanisms are MAR. Of course, whether that's a multiple imputation or single imputation doesn't matter, because most of the imputation methods, unless you do not have very strong assumption about the MCAR, normally people tend to have the MAR to avoid the modeling of the missing data indicator for a non-NMAR case. Okay, from this part gets more easier because there's not much of the theory already. Moreover, actually I kind of try to share my experience to do the imputation to the data sets. The KLoSA is the Korean version of the long-distance study of aging. So, well, aging problem is very serious in Korea too. And nowadays, due to the birth control, the population gets reduced very, very rapidly. And aging problem gets very serious. And they started the KLoSA to evaluate the aging trends and apply their findings to the social welfare and labor policy. So they actually sampled about 10,000 people from the 6,000 family. So from the 6,000 family, so actually 6,000 family was sampled, and so among the sampled family, the Koreans aged over 45 were recruited, and their target number was 10,000. Target sample size was 10,000. And the baseline study was conducted in 2006, and then their first follow-up was occurred 2 years later, and now they have the second follow-ups. And I will focus on imputation of the baseline as well as the first follow-up. And of course, as many other surveys, KLoSA also has missing values. And these missing values actually may cause the biased results. So we actually try to impute these missing values. And especially, of course, the KLoSA is quite a large scale of the study and have a lot of variables. Yes.
Well, I was just wondering, where did you get the questions you asked? Did you borrow from the U.S. longitudinal study on aging, or you made them all up out of whole cloth? Or?
Oh, actually, as I understand, they actually kind of get the information from both U.S. as well as Europe, and they built the study, which is very close to the U.S. as well as Europe, because they wanted to follow the world standards. So they can, they release the data, and they, once they follow the world standard, they can actually have good
compared to other studies.
yeah, good standard data set. So their data set is very close to the U.S. studies.
So, Juwon, how was the interview conducted? Was it mail-in, telephone, in person?
It was the in-person study, pretty much like the studies conducted here. So they actually recruited people, and then the interviewer actually visited them and did the study. And of course, we are interested in the major outcome variable, which is related with income as well as asset variables. This is the small summary. Actually include a lot more variables, but since we are interested in the income and asset variable, which normally has the larger misvalues. Of course, compared to U.S. data set, actually, Koreans have much lower missing percentages because the salary schemes are quite different between the U.S. and Korea. So people tend to answer more, but still actually income and asset related variables tend to have more missing values. For the design variable as well as demographic variables, the missing percentage is very small. But for the income variable, this is the percentage missing. This is the total observation. And this is the missing value, number of missing values, and this is the missing percentages. Of course, you can see this some portion actually has much smaller number of observations, because actually income just depends on their job. So some people get the job from the wage. So wage income is having the highest frequencies. But like this is the agriculture business income, and there are very few people actually works on that. So there are few people, but their missingness percentage is just less than 10%. But for the asset variable, which is the house price and the financial assets, they tend to have a more higher percentage of missing values. And for a few variables, actually missingness reaches up to about 30%. And this KLoSA data was consisted of 8 sections: cover screen, which just try to screen the eligible people, and have other 7 sessions. And we actually did the imputation session by session. Of course, we are more focused on the income and asset variables. And we started the actual imputation by the demographic section, because demographic section doesn't have much missing values and actually become the basic. And can be used as the covariates to impute the missing values. So demographic section was imputed, and health section is also imputed. Health section has a few missing values, and health is also related with the income, so it's imputed. And employment status was imputed, and then income and asset section is imputed. And of course, this family section is actually the money transfer between the family members. So sometimes old elderly people get the support from their children, especially popular in Korea. So actually, the money transfer is related in the family section, but we actually imputed this section at the end, because actually family sessions get sort of complicated, because, well, for the income, one family has one income, but for the family session, we actually measured money transfer for each family members. So if I have like a brothers and sisters, or daughters and sons, each one can give the money support, or I can give the support for each members. So those were measured here. So actually have more complication. So we use imputed this one at the end. And we use the 5, so we imputed this. Why 5? Depends on the missing information. And since we have actually not a lot of missing the percentages, we actually thought of 5 imputed data set would be enough. And we actually revalidate the missing information later. And then actually we choose the multiple imputation. And based on what methods? I already mentioned actually I used the compound method. But at the beginning, we didn't know actually which method would be appropriate for this data sets. So we actually did the simulation for the major variables. And chosen method is the hot imputation, but mixed with the explicit modeling, which is based on the predictive mean. Okay, before I discuss more, actually there is one specific characteristic of this income variable, actually pretty much similar in many US studies. Well, income is the problem is that people do not want to answer income very often. So instead of having just exact question about exact income, people often use the unfolding bracket questions, which means is first actually we ask the income of the person or of the family, and exact answer is given, that's fine. But if people refuse to answer the exact income and then ask these bunch of questions, called as the unfolding bracket. This means is actually we chopped income level as certain range, which is the bracket range. So if somebody actually refused to answer the income they asked, then is that more than 600? Then people can answer less than 600 or around that 600 or larger than 600. And then if it's larger than 600, then asks, is it more than 1200 and so on. So if some people answer for these unfolding brackets, we have more information, even though that's not the exact income.
Juwon, for that question, is it step question? That if you answer less than
Yes, so
600, you are done. You don't need
yes.
to answer for me.
Right. If this one is more than 600, and then
And
it's
then you
two.
answer.
Well, depending on the questions, sometimes people start with in the middle point,
it's
and then go
randomly.
to the left hand side and right hand side. And actually,
So the answer question is randomly selected.
as I remember, they start with that, but I'm not sure, 100% sure. And this is the summary. So among this wage income, about 1,900 people provided the exact income, but some actually did not answer. And they asked the unfolding question, 82 actually answered by the range. So even though we do not have the exact income, we have the certain range between these values. Of course, this is not exact value. So you have to do something for your analysis. And still, actually, some might refuse to answer, even for the range of unfolding brackets. So they kept as just missing. And this is the format. Pretty much most of income and asset variables were measured like that. And of course, we have kind of mixture of data values. Some actually some provided exact income, some didn't provide, but just provided range, and some didn't even have the information. And what kind of analysis I can do that? That's the question. Well, we have to do imputation using the information we have. So since we use the unfolding brackets, we have to use that information. And what that means is we know that the person's range of income. So for example, if someone's their income is between the 600 and 1200, this is the Korean dollar. So if they saw that their income is between 600 and 1200, our imputed values should be in that range. We cannot impute the value with the outside of the range. So we have to include that information for our analysis. So we have to incorporate information obtained from the unfolding bracket to conduct the imputation. But problem is, someone actually might just say my income is very high, for example, more than 12,000. And well, people tend to refuse the answer if their income gets higher. So for the people actually at the top end tend to refuse the answer more. And so for the hot imputation, you would have the top. So I will discuss how we handle that. But anyway, even though you do not have much choice, since you have the partial information about income, your imputation should handle that. And another thing is very important for the multiple imputation is you have to maintain the consistency among the variables. So if someone said, I have the wage income, and then actually they asked how many months they worked, and depending on the number of months they worked, their income different. So your data should be imputed separately. You have to impute the whole things consistently. So you have to have the consistency in the imputation. And using that in mind, we actually did some imputation based on several candidate imputation methods. First one was the random hotbed imputation, which means it's actually just a typical hotbed. Hotbed means that actually, since we do not know the value, we actually bring up the observed value. We actually place missing values from the recorded value of the data sets. So we have observed incomes, and among them, we choose the project value and impute. And good thing is actually imputation is in the appropriate range. But bad thing is actually for the unfolding bracket question, you have to have enough observed value in your range. If you have 3 missing persons, but if you only have 2 observed cases, you have enough. So sometimes actually people recommend to use other kind of technique for the case. Hotbed imputation is not allowed. So for the top open bracket, we may not have enough observed cases. Then actually regression type of imputation can be used. Actually, this random hotbed imputation is the imputation method adopted by the HRS data in the US. And luckily, they even provided the assess macro on their webpage, so you can try. Or another approach actually we chose is the hotbed imputation based on the predictive rematch. Difference between just the regular random hotbed and this one is, in the random hotbed, you just randomly choose one, but here, in the predictive, by using the predictive mean, actually you use the regression type of the model and try to predict your values. But do not impute based on the predicted value, but just use the predicted value to form the imputation class. So you have the predicted value and you divide the observation based on your predicted mean, and under the same subclass you do the imputation. That's the case. Actually have the assess macro, which is written in rand. And another nice approach actually we can use, and people use, and my experience, actually shows quite nice implementation. And frankly, we hoped actually we could use this method when we did the simulation because this one was faster and easier to apply. This is called as sequential regression multiple imputation, which is the imputation based on the sequence of the regression model. So since we have a bunch of variables which has different types, we cannot assume that is the normal distribution. So instead of that, actually we try to do the sequence of the regression based on the appropriate model. Like for the continuous variable, normal regression model. For the binary variable, logistic regression model. For categorical variable, generalized loading model, and so on. So for each variable, we know that the type of the variable, and conditional on the rest of the other variable, we can fit the appropriate type of the regression, or logistic regression, or generalized regression model. And the imputation, it totally. Actually, their concept is we have to have the sample based on this joint distribution, which means expressed as like this kind of joint distribution. But unfortunately, this is the condition. Which one should come to the first one and second one? So instead of doing that, actually what they did is they actually generate data set. Why generate missing values for the jth variable given the rest of the other variable. Of course, this joint distribution and this joint distribution is different. So actually use the SIR algorithm to improve the approximation between this difference between this and that. And they actually have the free program, SAS macro program called as IBWare. I heard actually this type of the model is also implemented in Stata as well as other softwares. And good thing for this is actually this program also allows to handle the missing values within the certain limited range. So actually can be used for our case. So we say that this person's information is between the income information is provided by the unfolding brackets. So I have to say you have to impute the values within this range. That's possible. So we use those three. And did the simulation. And for the simulation, I have to finish quickly, so I will quickly do this. I consider the initial respondents as our population, and randomly sampled 250 individuals from male and female, because male and female income and assets are quite different, so separately. And then actually we use the logistic regression to predict the probability of missingness. So actually follows the missingness, so become very close to the MAR. And then we made 2% of missing values. Among the 10%, we actually divided as half and considered them as just totally missing, and other half were considered as providing the unfolding bracket information. And did the imputation based on random hardware. This is the one we took hardware imputation based on the predictive matching and sequential regression imputation. And in addition to that, actually we also compared two simple ones. First one is the complicated analysis, which ignores all missing values, and also sometimes called as a midpoint or median imputation, which means is if you have the unfolding bracket information, you just pick the median value and put it out. Simple results is here. So this all data is the data without any missing values. Before we making the missing values, so this is a mean. This IBWare is the sequential regression. This is the hardware based on predictive mean matching. coverage was quite good for this data set, all these cases. But well, compared.
Bias is a percentage. Oh, that's just the amount of.
Yes, this is just the amount of bias, but we also provided well, calculate standard bias as well as others, but have the coverages as well. And well, we compared a bunch of variables. Some worked better for this method, some worked better for the other methods, and our experience is pretty much all these three methods worked quite well. And especially the imputation we chose based on the predictive mean matching worked very, very well. And this one, sequential regression imputation, also worked very well. And we chose this one because it showed smallest bias.
Juwon is the last one, coverage is only 10.7.
Yes, so for sometimes we found that sometimes this method, this method is based on the random hardware. So for some variable actually worked very poorly, and some variable worked very fine. So we kind of debated between these two. So as I mentioned before, this one is easier to program, so we managed to cheat this, but this one actually showed a smaller bias with hardware based on the predictive mean matching. So we actually did the imputation algorithm just pretty much. And this is the observed histogram of the observed data and cubic data set. You can see actually quite difference between the cubic data set and observed data set because the income tend to be more missing for the high income. For the follow-up, actually, follow-up data was the imputation was quite simple in this case because, well, for the follow-up data set, actually, you have two different missingness. One is called as unit non-response. The other one is item non-response. What means is actually some participant actually answered for the baseline, but for the first follow-up, they didn't answer. But that kind of unit non-responses were handled by the weighting method. That was their decision. So original data has the weight, and for the follow-up, somebody might not answer, and then they give the reweighting. So new weights are given. So unit non-response was handled by the weighting response. So we actually only handled the item non-response. So since we use the hard imputation based on the predictive mean matching, we use the same method to be consistent. But since actually earlier baseline variables are very good predictor for the follows. For example, like income on SF doesn't change a lot over time. Of course, they will increase or decrease a little bit. But since actually baseline values would be very highly correlated, we actually include that the imputation model to calculate the predictive mean. And these are missing percentages. So actually missing percentage was even less than the baseline because once people try to answer, they tend to answer more. And this is the comparison between the observed and empirical. So I will quickly finish. So we did the multiple imputation. Well, how we choose the imputation model is very important. And what we've done is we did the simulation based on the fully observed cases. And we kind of mimicked the missingness as we really observed and chose several candidate imputation model appropriate for this case and did the imputation for the major variables and chose the imputation model. Actually, the special thing for this KLoSA study was we actually extended hard imputation to handle the onboarding bracket. I never saw the case actually hard imputation based on the predictive mean matching is extended to this case. So we did that. And actually, if we cannot find enough observed case, we call that donor. And then we actually incorporated regression imputation to impute the possible values. And we try to reserve the consistency among the variables, so have several approaches. And also, next one is briefly discussed here. So we actually adopted a new approach for the family session. Because for the family session, as I mentioned before, we asked monetary support for each member. So if someone has 2 sons and daughters, we asked how much they give to the son and how much they give to the daughter. Of course, the values are related to each other because your total amount is limited. So we have to incorporate dependency of the observations. So we used actually GE method to calculate the predictive mean in this case, to include the relationship between the observations. And actually, Yoon was my student, wrote the master's dissertation about the Hadley imputation based on the multi-level models. So using the random effect model, calculated the predictive mean, and based on that, did the Hadley imputation. And she actually compared the case. Actually, this math approach works better than the normal type of the multi-level imputations.
So Juwon, quick question about that financial support. So you would ask the participant who's older than 45, right?
Right.
So it's like how much money that person gives to their sons and daughters. Do you collect how much they receive from their like sons and daughters?
Yes.
And then is there like a time frame in terms of, is it like within the past year?
Yes.
Okay. Because I think in Korea there might be some seasonal like variations. Like I remember like growing up, like during like Korean New Year's and Full Moon Festival, people come. If the sons and daughters are out of town, they come and give money to their parents. So depending on when the question was asked, there might be some variation in responses.
Yes, actually they asked both regular and irregular.
Okay.
So especially like the special occasion,
Right.
like that kind of special season, or like the case actually the sons and or daughters get married. The parents actually tend to give some large money, so they actually separated that
Okay.
question.
Juwon, I don't quite understand the GE here. You don't really consider any standard error, right? So what GE plays a role here for predictive mean?
Well, to calculate the predictive mean, actually standard error is
Oh, this is the result, how you analyze the result.
yeah.
Now imputation model.
No imputation. The only part actually related to is since we use the hot imputation, we have to calculate the predictive mean, and based on the predictive mean, we actually divide the subclasses. So doesn't have much actually. Well, kind of we are in the kind of in the safe area in some sense because our prediction really doesn't influence directly. But still, actually, your primary estimates are also related with the variance parts, so slight difference actually. And another thing is actually we kind of actually handle the categorical variables, so like a binary variable, by using the logistic regression instead of the regular regression. Top part is how about the nominal variables? If we have like 3 categories, which is nominal categories, your predicted value is not one value. You're just calculating the predicted value of one category over the other categories. And how we incorporate those information to the hotbed to actually make the subclasses. That's kind of things that I think nothing has been done, and maybe actually can handle that as pretty much similarly like the multivariable cases. Some of the extension might be possible. And another thing is actually for the unfolding brackets. This is the final one. For they asked about 600. We didn't have much choice, so we just imputed with 600. But about 600 does not mean exact 600. It can be 550. Or some people might just say 500. So how we handle this is another interest. And as I remember, I reviewed one article submitted for the journal. They actually suggested one kind of how to handle this, but they didn't provide any simulation. They just had some kind of idea. And I looked at it again and hasn't published yet. So the how to handle these kind of above values is also worth to pursue for the analysis. Okay. Thank you, and I'm sorry to be late, and thank you very much for attending this. Thank you for giving me the presentation.
Ran over. Ken was just asking one question, which is how is multiple imputation in Korea, is it really well established, like it does seem to be here now, or is it still catching on? How would you characterize that?
Actually, my understanding is this is the first study actually applied multiple imputation. Before actually, many studies, many Korean studies actually use the imputation techniques, but they always stick on the single imputation. And I kind of try to explain what's the problem with the single imputation and how you have to handle that, and also gives a lot of presentation about the multiple imputation. Or if you have to stick on the single imputation, what you have to do, that's a very important part. But actually this one, some researchers, some PIs actually was hesitating to do the multiple imputation. But this PI was quite open for that, so adopted the multiple imputation. And I think this is the first one, and nowadays actually people try to understand more about the uncertainty related with the single imputation.
Maybe we'll let people break.